Who's ready for some rational functions? I know I am. We're going to have so much fun learning about all these nifty properties and characteristics about graphs of rational functions in different formats. So get ready because it's going to be one exciting unit. Come on, thing. Alright, so remember whenever we have a function, we always have a parent function, which is the start graph. Okay, which a rational function in its most simplest format is y equals 1 over x. Nothing is added, subtracted, multiplied, or divided to a fraction that we have here. And rational functions, x must be at least in the denominator of the fraction. So this is the simplest format that we have for a rational function. Now, here's the graph, which it looks kind of cool, right? There's like two parts to the graph. Kind of got this part that's going like this is like that, and then this part's like okay, so we have kind of two parts of the graph when we have a rational function, which is kind of hard to tell, but if you zoom in closely, do you see these green and kind of bluish purpley lines on the y and x-axis? Well, guess what, you guys? Those are actually going to be asymptotes. Okay, which let's see if I can zoom out. This thing is not cooperating. Sorry, guys. Come on, thing. Alright, so there is a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. So this thing has two asymptotes at the same time. Holy hot dog, right? Okay, so our horizontal asymptote on the x-axis is the equation y equals 0. Remember, horizontal lines are always y equals a number. And I always remember that by horizontal. Y equals is a horizontal line, so I just combine the y and the h to make a horizontal line. And it's where the x-axis is 0, or where if you were to draw your horizontal line, it hits the y-axis at 0. Okay, and your vertical asymptote is x equals 0. Vertical lines are always x equals a number, and I remember that by zertical. I combine my v with the x equals, which makes zertical. And then it tells me wherever it hits the x-axis. It hits the x-axis at 0 when it crosses it. Okay, so it's where x equals 0 and y equals 0. Now, let's think about this. Why does a graph that's 1 over x have a horizontal and vertical asymptote at y equals 0 and x equals 0? Okay, so in class, I got you guys to think about these questions, but I'll go over it again in case you forgot or you were not there. Okay, so why can x never equal 0? Okay, because we have a vertical asymptotes and horizontal asymptotes because the graph can never equal those values. It gets super close to the x-axis and super close to the y-axis, but it can't touch it. So let's think about why this happens. So why can x never be 0? Well, if I put in a 0 for x, we'll be dividing by 0, which is definitely not allowed, you guys. That's when we start killing kittens, okay, which is definitely not allowed. So that's why there's an asymptote on the x-axis, because x can never be 0, never, okay? So that's why. Now, why can the function 1 over x never equal 0? So why can the y not equal 0? So let's think about this. If I put 0 in for y, okay, I want to think 1 divided by what will give me 0. So let's see here. 1 divided by 4, no, that's 0.25. 1 divided by 10, no, that's 1/10, or 0.10. Well, 1 divided by 1,000, well, that's 1/1000th. Okay, I can keep doing that, and I can get smaller and smaller, smaller. I can do 1 divided by 1,000,000, and it's still not 0, you guys. We get really close to 0, but it never equals 0. So y can never equal 0 as well. That's why there's an asymptote on the x-axis. Okay, so there's an asymptote on the y-axis because x can never be 0. And there's an asymptote on the x-axis because y can never be 0. Okay, so let's think about what the domain and range would be for this function. So if we think about the x values, so the graph goes off to negative infinity for forever. This arrow keeps extending this way. Okay, and it goes off into positive infinity for forever. So we're hitting all the values, right? Not quite. We go left for forever and right for forever, but the only value that is not allowed on the x-axis is 0. So your domain cannot be 0 on the x-axis. Same with the y. The y heads down to negative infinity. It heads down here. Sorry, I'm trying to hit it. That keeps popping up. Okay, so if you see on the graph, it kind of heads down to 0, but for some reason this thing is acting up. I don't know why. Let me see if I can fix that. Stop that. Okay, so it heads down for forever. Okay, and it heads up for forever. This arrow is heading up for forever. So that means it goes from negative infinity to positive infinity, right? Well, no, because this asymptote on the x-axis blocks 0 on the y. So your x and your y cannot be 0, you guys. So for your domain and range, x cannot be 0 because there's an asymptote sitting there, and y cannot be 0 because of this horizontal asymptote sitting here. Okay, so simply in inequality notation, you can say the domain is x cannot equal 0, and the range is y cannot equal 0. Or if you like interval notation, it's a little bit trickier for interval notation. So we kind of have to take it in chunks for interval notation. So we look at this piece on the left for the domain. It heads off to negative infinity because it heads off in this direction for forever. So when we say how far left does it does go to negative infinity. And then how far right does this piece on the left side of the graph go? Well, this piece, it gets really, really, really close to 0 on the x, but it does not touch it. So we do a closed bubble, and then we kind of have a separate piece that is not associated with this piece. This is why the little u thing. So the domain on this one, how far left does this piece go? Well, it gets really close to 0 on the x, but it does not touch. So that's why we use a 0 with a parenthesis. And then when we say how far right does it go, well, this on this end is headed off to infinity and beyond with Buzz Lightyear, so to positive infinity. So the domain and range kind of had two pieces when we do this. Same with the range. If we look at this piece, how low does this piece go? Well, this is shooting off to negative infinity down here. If this thing would get out of my way, get out of my way. But anyways, it heads down to negative infinity. And then on this piece, when we say how high does it go, well, it heads really close to 0 on this side, but it does not touch 0 on the y-axis. So that's why we have negative infinity to 0. And then the second piece, which is not associated with this piece at all, they are not connected. That's why we have the little u thing. When we say how low does it go, it gets really close to 0 on the y, but it doesn't touch because of this asymptote sitting here. And then when we say how high does it go, well, it shoots off to positive infinity on this side. So that's kind of why the interval notation looks really weird. Okay, but when we have parent functions, we always can move away from the parent functions, which is when our transformations come in. Okay, which, like we've been doing, you guys, transformations never, ever, ever change. So when we talk about the a, the h, and the k value, they do the same things as our previous functions. Okay, so although they're kind of located in different locations, so kind of be careful with that. Sorry guys, this thing's really bothering me. Let me see if I can fix it. Stop it. No, stop. Okay, I'm going to get away from it so it doesn't do that again. Okay, anyway, so our a values, whatever the number is on top of our fraction, so the numerator is the a. The h is added or subtracted to the x in the denominator, and my k value is just added onto the end of the fraction. So it's kind of like by itself, not really associated with the fraction. So what does the a value do, you guys? I already know you know. Okay, well this is what the a value does, which you've heard this before, so it should be a review. When your a is negative, it will reflect over the x-axis, so flip upside down. When a is greater than 1 or less than negative 1, okay, remember whenever your a or your b is not a fraction or larger or smaller than negative 1, it always gets skinnier. So vertically, if we think about something vertically that gets skinnier, you have to stretch it up vertically to make it skinnier. So it's a vertical stretch. And when it is a fraction or in between negative 1 and 1, your graph gets wider, which if you think about compressing something vertically, smushing it down vertically, it will make it get wider. Okay, so same thing as before. Complete review. Okay, and then your h and your k value, you guys remember. Remember the h value, you have to think the opposite. You have to. So if it's x minus h, it goes to the right that many spaces. And if it's x plus h, it goes to the left that many spaces. Okay, and the k value, you do not think the opposite with. So positive k goes up, negative k goes down. Who's ready for some example problems? I knew you guys were. Let's get going. Okay, so all we're going to do is identify the transformation. But before we do that, we have to know if there is an A, H, or K in the problem to know where the graph is going to move away from its beautiful parent function that we saw over here. So this is the start graph, and all these transformations are going to move it in different ways. So let's see what's going to happen. Let me go back. Alright, so for this first one, we have a -2 in the numerator. So is that an A, an H, or a K? Holy hot dog, you guys are so smart. It is an A value. Okay, and since the A value is negative, what is the graph going to do? It will reflect over the x-axis. So remember, a negative A value reflects over the x-axis. And since this 2 is either less than -1 or greater than 1, which it's less than -1, it will be a vertical stretch because it gets skinnier. Yay! So that is the transformation. Awesome, right? All right, example 2. Is this +2 right here an A, B, H, or K? Okay, which actually we don't even have B values in this, you guys. The B value is a little bit overly complicated, so we don't deal with the B value with transformations, and we have a rational function. So what we need to decide is if it's an A, an H, or a K. You guys are so smart. The 2 is an H value. Okay, which the H, you have to think the opposite. And remember, H, we think of our hips, which go left to right. Okay, so the H value, since it's a +2, will go left 2 spaces, so be careful. And finally, is this -2 down here an A, H, or K? Well, it's on the end of the fraction, and it is added or subtracted. Okay, the H value has to be added or subtracted to the X. The K is kind of like off to the side, has nothing to do with the fraction. Okay, so this is a K value. And remember, the K value, we do not think the opposite. It either goes up or down. Remember, we think kangaroo goes up or down. And since it's -2, it will shift down 2 units. Holy hot dog, right? That was awesome. Example 1, 2, and 3 are donezo. So these are example problems, you guys. I think I forgot to mention that, but they are example problems. So make sure you do write these down in your handy dandy notebook. All right, now let's talk about the parent function and what is going to happen to our asymptotes in domain and range when we have the parent function. So this is our parent function. Now, when we apply transformations to the parent function, we need to think about what's going to happen to our asymptotes when they move and what will happen to our domain and range. So in class, we talked about these questions, but I'm going to talk about them more in depth right now. So when you apply the H value, and move the graph left or right. So an H value shifts this thing left or right. Okay, which asymptote is going to move if the entire graph moves left to right? You guys are so smart. It is the asymptote on the y-axis, which is our vertical asymptote at x equals 0. Okay, so whenever we move left or right, okay, it will shift this vertical line. Now, the reason why it doesn't shift the horizontal asymptote, since the horizontal asymptote's already headed left to right, if you move it left to right when it's already headed left to right for forever, it's not going to move, right? Okay, so when you go left to right or move your H value, okay, your vertical asymptote's going to move. Okay, so this means that actually what's going to happen is your vertical asymptote is going to end up being the H value, because if it starts at 0, because this is technically like x plus 0, okay, if we move it left or right, the asymptote will also move left to right that many spaces. So our asymptote is actually going to be, our vertical asymptote is going to be x equals our H value, which is pretty cool. Okay, which will also affect the domain. Since the domain directly relates to this vertical asymptote right here, okay, it will also be where the asymptote moves to, which is our H value. So the domain will not be able to equal whatever the H value is, because that's where the asymptote will be sitting. Okay? And then when you apply the K value and move the graph up or down, which asymptote moves? So if we move this graph up or down, which asymptote do you think will shift? You guys are too cool for school. It is our horizontal asymptote. Okay, the vertical asymptote is already headed to infinity and beyond, up for forever, and down to where the demon cats lurk, so watch yourself. Since it already heads up and down for forever, if I shift it up or down, it's not going to move. So if you move a graph up or down, the horizontal asymptote will be affected, or the line y equals 0. Okay, so when you move it up or down by the k value, the asymptote will also shift up or down that many spaces. Okay, so what that means is your horizontal asymptote is going to be y equals our k value now, because if we start at 0, if it goes up or down as many spaces as the k value, that's where the asymptote will be sitting. Okay, which this is going to affect our range because it will be where the asymptote is now, okay? Which if the asymptote moves, the range cannot equal that value. So the range will be y cannot equal whatever the k value equals. Okay, so if that doesn't make sense, just remember you have to follow these rules. Okay, when your rational function is in this nifty format, okay, your vertical asymptote is the equation x equals h. Okay, so once you identify the h, which remember we have to think the opposite with our h value. So if this is a negative h, it's going to be a positive h here. Or if it's a positive h, it'll be a negative h here. Okay, so our vertical asymptote is whatever the h value is. X equals h. Okay, the horizontal asymptote is going to be y equals our k value because that is where the horizontal asymptote will have shifted. Alright, which this will affect our domain and range. So now our domain will be whatever x cannot equal wherever the asymptote is, which is that h. So x cannot equal h because there's an asymptote sitting there, which means the graph can never equal it. And the range will be y cannot equal the k value because that's where the horizontal asymptote will be sitting. So the graph can't equal it. Okay, so basically when we do this, what we're going to do is we're going to identify the h and the k, which that will be where our vertical asymptote is and our horizontal asymptote are. And in the range, we just say x cannot equal whatever the vertical asymptote is, and the range will be y cannot equal whatever the horizontal asymptote is. Who's ready for our next example problems? It's going to be exciting. So make sure you copy down example 4 and 5. We will be identifying the horizontal and vertical asymptotes and then state the domain and range. Okay, so on this one, let's identify the horizontal asymptote. Actually, let's identify the vertical asymptote first. Okay, so our vertical asymptote is whatever the h value is. So, vertical asymptote is our h value, which remember we think the opposite. So let's see here. Where's the h value in example 4? Holy hot dog, that's where it is, right there. So currently it's x minus 2, so the h value we have to think the opposite. So since it's minus 2, your vertical asymptote is going to be x equals positive 2. Okay, so think the opposite with your h value. Okay, now the horizontal asymptote is wherever the k value is. Where's our k value? Holy hot dog, it's right there. Okay, so the horizontal asymptote is y equals the k value. So our k value is 9, so it's y equals 9. And then all we do for the domain and range, we just say x cannot equal our h value, and the range is just going to be y cannot equal the k value. So our domain, our h value is 2, so we just say x cannot be 2. And for the range, we say y cannot be our k value, which is 9. So y cannot equal 9. And that's it, you guys. Don't overthink these. As long as you know the h and k value, you are good to go with these problems. Okay, and let's take a look at the graph, because these graphs are really cool. Okay, so this was our equation. Okay, the blue dashed line is our horizontal asymptote at 9, and the green dashed line is our vertical asymptote at 2. Doesn't that look cool? So the graph kind of like follows the asymptotes. It gets really close to each asymptote, but it does not touch it. Okay, I always kind of think of the asymptotes as like little magnets. The graph wants to get super close to it, but it never touches it. And they do it on both ends, which is really cool. Okay, so for our next one, example 5, if you think you understand this, go ahead and pause the video, do it on your own, and see if you end up getting it right. Okay, as long as you know the h and k, you're golden. So our vertical asymptote. Where is the h value in example 5? It's right there. Holy hot dog, right? So our vertical asymptote is x equals, now we think the opposite. So since it's a positive 7, it will now be a negative 7. So x equals negative 7. The horizontal asymptote is wherever the k value is. So, where is the k value lurking? Right there. Bam! Okay, so our horizontal asymptote is at y equals negative 3. And the domain is where x is basically, it cannot equal the h value, which is negative 7. So x cannot be negative 7 for our domain. And for our range, we say that it's whatever the horizontal asymptote can't be. So since our horizontal asymptote is at negative 3, our range is y cannot be negative 3. Come on, thing, cooperate. Sorry, guys. Cooperate. Sorry, y cannot equal negative 3. And that's it for example 4 and 5. And here's our nifty graph for this one. So this is our equation. Okay, here's my x and my y axis, if that helps. Okay, so we have a vertical asymptote at x equals negative 7. It crosses the x-axis at negative 7. And we have our horizontal asymptote at y equals negative 3. It hits the y-axis at negative 3. And see, our graphs kind of navigate toward those asymptotes. They kind of are attracted to them. They get really close to each side, but they don't touch. These are some of my favorite graphs, you guys. You're going to get a kick out of these graphs. Alright, so now we'll be finding vertical asymptotes and zeros for rational functions. But now, we are moving on from transformation notation. So what we are working with before, you guys, this notation right here, when we're in this format where it's a divided by x minus h plus k, that's when we have transformations. Now we will not have something that looks like this, which I'll show you that in just a moment. Okay, we are now strictly working in our just standard rational format. We're going to have a polynomial divided by a polynomial. And you'll see how this is not in our transformation form. You'll see in just a little bit. Okay, so the steps we'll be doing on these. The first step will be factoring the numerator and denominator. So since we're kind of back into our normal standard form of rational functions, we had to go back to doing all that lovely factoring. So we'll be factoring the numerator and denominator when we do this. Then to find the vertical asymptotes, sorry guys, this thing's really not cooperating right now. To find the vertical asymptotes, what we're going to do is we're going to set each factor in the denominator equal to 0 and solve for x, which I'll explain why in just a moment. And to find the zeros is kind of the reverse. We're going to set each factor in the numerator equal to 0 and solve. So if you see, you guys, this does not look like that a over x minus h plus k. Does not look like it at all. Okay, so if it is not in that simple transformation format, these are kind of the steps we're going to be following. So kind of ignore what I've been telling you when you look at this. Okay, so in a moment, you will be watching the video on example 6, because I will not be doing it on the Prezi for you. But let me explain why we set the vertical asymptotes, why we set the denominator equal to 0, and the zeros, why we set the numerator equal to 0. So for the vertical asymptotes, this is where the function is undefined. Okay, vertical asymptotes occur where values of x are not allowed. That's why we have an asymptote there. So what value is never, ever, 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 ever allowed in our fraction? What can never equal 0? It's our denominator. Our denominator can never, ever, ever be 0. That's why there secretly is an asymptote sitting there, because the graph can never equal it. Okay, so that's kind of why we set the denominator equal to 0 for a vertical asymptote, because vertical asymptotes occur where the graph is undefined. Now the reason why we set the numerator equal to 0, okay, when we find zeros, we set y equal to 0 and solve for x. So that means, imagine this f of x is now a 0. So we have 0 equals all of this. Okay, well, say that I multiply x minus 2 on both sides. So if I multiply x minus 2 on this side, it'll cancel out. If I multiply x minus 2 on this side to 0, because remember f of x turned to 0, it will turn to 0. So we're left with the numerator, or x squared minus 2x minus 3 equals 0. So that's kind of why we set the numerator equal to 0 to solve for zeros, and why we set the denominator equal to 0 for vertical asymptotes. Which, if that doesn't make sense, you guys, just know that this is the process we use, and just kind of ignore what I said. Okay, but anyways, go ahead and pause the video, watch example 6, and see how to find vertical asymptotes and zeros in our standard rational function format. Have a blast. Well, I hope you had so much fun finding those vertical asymptotes and the zeros, which I want you guys to see what the graphs look like, because they're pretty cool. So if you look here, let's see if I can zoom in anymore. Here's our graph. Okay, the blue dashed line is our vertical asymptote at x equals 2, and the zeros we found to be at -1 and 3. So that's kind of what the graph looks like. Doesn't that look cool? So on this side, see how it kind of heads toward the asymptote? It kind of navigates toward it and gets really close. And same over here. When it's near the asymptote, it kind of gravitates toward it. Okay, it kind of wants to get really close to it. So that's what that looks like. Pretty cool, right? Alright, now for example 7, go ahead and pause this video and watch the example 7 video to learn how to find the asymptotes and zeros, which, if you think that you already know how to find the vertical asymptotes and the zeros, go ahead and try it on your own and then see if you get the same answer as what I get in the video. Holy hot dog! Wasn't that so much fun, you guys? Example 7 was a blast, and this is what the graph looks like. So for this one, there was a vertical asymptote at x equals -3, which, see the graph, again, it gravitates towards the asymptote on this side, and this side it gravitates toward it. Okay, and then the zeros are at -6 and -1, which is pretty exciting. Alright, now, horizontal asymptotes in our standard rational function format. So again, we're not in our transformation format anymore, so ignore what I said at the beginning. Okay, when it's in this typical standard form for rational functions, there are 3 rules for identifying horizontal asymptotes. And it's all based on the degree of the numerator and the denominator of your fraction. So if you know the highest exponent in your numerator and you know the highest exponent in the denominator, guess what? The horizontal asymptote will be super, super easy to identify. So we have 3 rules. There's only 3 possibilities for a horizontal asymptote. The first possibility, if the degree of your numerator is larger or greater than the degree of your denominator, there will be no horizontal asymptote. You will not have any horizontal asymptotes, which is sad because we always want our graphs to have horizontal asymptotes, right? Case 2, it's the reverse. If the degree of the denominator is larger than the degree of the numerator, we have a horizontal asymptote at y equals 0, which is the x-axis, if you didn't know. Okay, that's always the line where all of your y's are 0. But anyway, so if that's the case, it is always the equation y equals 0, or your x-axis, always. So that one's pretty easy. Now the third case, say your numerator and denominator degree are equal. Well, there's a nifty formula that you use when the degree of your numerator is equal to the degree of your denominator. What you do to find the horizontal asymptote, which since we're horizontal, we're horizontal, which means we're y equals, okay? So y equals, you're going to take the leading coefficient of the numerator and then divide it by the leading coefficient of the denominator. And that's it. So whatever those 2 leading coefficients are when you divide is your horizontal asymptote when the degrees are equal. So you just have to be able to identify the degree of the numerator and and the denominator, and then you just pick one of these 3 options. Okay, that's it. Don't overthink these, you guys. So we will be identifying horizontal asymptotes only in this situation using these 3 rules. So in our first one, we start by identifying the degree of the numerator and denominator, which we are now in example 8, you guys, so you need to get out your handy-dandy notebook and copy down this wonderful example problem. So example 8, the degree of the numerator. Now, what is our highest exponent we see? It is a 2, you guys. The highest exponent I see is a 2, so the degree of the numerator is 2. Now, what is the highest exponent of my denominator? Well, I don't see an exponent, so secretly the x has a 1, and that's going to be the highest exponent. So the degree of the denominator is 1. So since the degree of the numerator is larger than the degree of my denominator, what that means is there will be no horizontal asymptote, which is sad. Okay, we're following this first rule. The degree of the numerator is larger than the degree of the denominator, there's none. Which is sad, I know, right? We wanted it to have a horizontal asymptote. But I'm still going to show you the graph because it looks cool. So if you see here, there's not some horizontal line that the graph kind of navigates toward, or gravitates toward, I guess that's the better word. There's not really any horizontal line that any part of the graph is going toward. So it might have a vertical asymptote, but now we're just talking about horizontal asymptote. So we're sad because there's not a horizontal asymptote, but it'll be okay, you guys. I have faith in my next example problem. I have so much faith in it. So let's talk about example 9 now, which this is also in your handy dandy notebook. So again, we start by identifying the degree of the numerator and the denominator. So what's the highest exponent in the numerator? It's a 2. So the degree of the numerator is 2. What is the degree of the denominator? Holy hot dog, you guys, it is a 2. Okay, so if we look here, the degrees are equal. They're the same number. So when the degree of the numerator is equal to the degree of the denominator, that's when we get to use that nifty formula where we divide the leading coefficient. I abbreviated it with LC. So we divide the leading coefficient of the numerator by the leading coefficient of the denominator. So we're following this rule 3 right here. So let's figure out what the degree of the numerator is. Let's figure out what the leading coefficient is of the numerator. Sorry, you guys. So the leading coefficient is the coefficient of the term with the highest exponent. So the highest exponent term is this 6x squared right here. So our leading coefficient is a 6 here. And in the denominator, our leading coefficient, the coefficient of the term with the highest exponent term is 3x squared. So the leading coefficient is the 3. So all you gotta do is take the 6 and divide it by the 3. That's all you do. You just divide the leading coefficient of the numerator by the leading coefficient of the denominator, which 6 divided by 3 equals a 2. So our horizontal asymptote is just that y equals 2. Fun times, you guys, right? And here is our lovely graph. So if you see here, we have this blue line right here is our horizontal asymptote, which, see, it crosses the y-axis at 2. Okay, it's a y equals 2. But something funky is going on here. If you think back, Miss Long told me a little while ago that asymptotes are things that the graph gets really close to, but never touches. Holy hot dog, do you guys see this point right here? What did the graph just do? It crossed the asymptote. Oh no, this graph is a little cheeky right now. It's pretty brave to cross through a horizontal asymptote. Okay, so I have to admit, Miss Long was lying to you guys. I know, I don't like to lie. I was just hiding part of the truth from you. But horizontal asymptotes are the only kind of asymptote that a graph can cross. Okay, I'm not lying anymore. Okay, I'm out in the open. The only asymptote that a graph can sometimes cross is a horizontal asymptote. It can never, ever, ever cross a vertical asymptote. So don't you worry. Okay, but isn't that cool? So the graphs right here gets super close to our horizontal asymptote at x equals 2. It comes down, it crosses through the asymptote. That's when it got brave and it sliced through the asymptote. But if you guys see, even when it crosses the asymptote, it still really, really wants to get close to it again. So it kind of heads back down to get really close to it. So regardless of it crossing through, it always gravitates towards that asymptote. It's like a magnet. Even though it crossed through the magnet, it gets really close again. So it was brave, but it still kind of failed because it still wanted to be really close to the asymptote and not cross it. It can only cross it one time, you guys. It's not like it can just keep crossing. So this was this one-time chance, and that's all it gets. Doesn't that look cool? Okay, so let's talk about our third example that involves horizontal asymptotes. So we're on example 10. If you guys think you understand how to do this, pause the video and see if you get it right. We're just following these 3 rules up here. Okay, so again, we identified the degree. What's the degree of the numerator? Holy hot dog, it is 1, because if I don't see an exponent, there's secretly a 1. What's the degree of the denominator? It is a 2. So now the degree of the denominator is larger than the degree of the numerator, sorry. And when that is the case, when the degree of the numerator is less than the degree of the denominator, or you can reverse it, when the denominator is larger than the numerator, the asymptote is always y equals 0. And that's it. That's all you got to say. If that's the case, when the denominator is larger than the numerator, it's always y equals 0. That's it. Okay, and I wanted to show you guys the graph so I can manipulate the graph, because this is another brave graph where it crosses through our asymptote. Okay, so if you see here, we have 3 parts of the graph, which is cool, which this graph is actually going to have some vertical asymptotes in it, but for now, we're just focusing on horizontal asymptotes. So if you see, there's a horizontal asymptote at y equals 0. It crosses the y-axis at 0. So on this side, see how it gets really close to 0, but it does not touch it. Now on this side, it breaks the rules. If you see here, it crosses. Okay, it does cross, and it kind of starts to head upward. See, it's kind of getting close to like point, let's see here, what are we at? I don't know, we're a fourth of 0.2, so we're at a really small number. But anyways, we're getting really close to this first line right here. But then if you see, the graph always gravitates back towards that asymptote. So I just wanted to show you guys this. If you see, the graph it goes up on this side. If you look over here, it heads up and it gets pretty close to that first line, but then it starts going back down. It's kind of hard to tell, but if I keep going over here, if you notice, it's getting back down to that horizontal asymptote. It gets closer and closer and closer and closer, and now it kind of looks like it's on top of the asymptote. See, so even though it crossed through at one point, it still navigates or gravitates back toward that horizontal asymptote. And see, it's still not touching it, but it's still, each time I slide it over, it gets closer and closer to that asymptote, which is kind of hard to tell. I would have to zoom over a lot, which here I'll zoom out and scroll over so you can see. So if I go over a bunch again, see, it just keeps kind of wanting to get closer and closer to that horizontal asymptote. So I just wanted to show you guys that because I thought it was kind of cool. But anyways, yeah. So that's kind of what that graph looks like, which is pretty awesome. All right. So now, So now we are combining everything we've talked about in our standard rational function format. So again, we are not thinking about those transformations anymore. Okay, so for example 11, okay, we're going to identify our horizontal asymptotes using those 3 nifty rules. Our zeros by setting the numerator factors equal to 0, and our vertical asymptotes by setting our denominator factors equal to 0. So go ahead and pause the video and watch example 11. Oh man, example 11 was exciting, and this is what the graph looks like. So I'd like you guys to see these awesome graphs. Okay, so if you see here, we have a vertical asymptote. It's hard to see, but there is a blue vertical asymptote right here sitting on the y-axis, which is the equation x equals 0. Vertical lines, there's vertical, x equals 0, and it crosses the x-axis at 0. That's why it's x equals 0. This one did not have any horizontal asymptotes, which if you see, there's not some horizontal line that the graph kind of goes toward. And our zeros are at -3 and 2. Pretty cool, right? All right, now we're on to example 12, which again, if you thought you understood example 11, go ahead and pause the video and try it on your own and then see if you get it correct. Otherwise, follow along with me in example 12. Oh man, you guys, example 12 was awesome, and again, I like to show you guys the graph. So this is what our graph looks like. Okay, we had a vertical asymptote on the y-axis at x equals 0. It crosses the crosses the x-axis at 0. And we had a horizontal line at y equals 0. It crosses the y-axis at 0. And our 0 was at 1. Which, this one was a brave graph. It crossed through the sorry, I cannot talk today, you guys. I don't know what my deal is. It crosses through the horizontal asymptote, but then if you see, it navigates back towards it, which is cool. So horizontal asymptote at y equals 0. vertical asymptote at x equals 0, and you have a 0, it hits the x-axis at 1. Alright, we got one more like this, you guys, so go ahead and pause the video and try out example 13. If you want to try it on your own, I highly encourage it. Otherwise, follow along with me. Oh man, you guys, this is one of my favorite graphs of the entire Prezi. Look at that graph. Isn't it awesome? It's got like 3 different parts to it, and it has all these horizontal and vertical asymptotes in it. It's cool, right? Okay, so on this one, we had 2 vertical asymptotes. Holy hot dog, right? We had one at x equals 2. It crosses through the x-axis at 2. And we also had one at x equals negative 2. So it crosses through the x-axis at positive 2 and at negative 2. And then we had a horizontal asymptote at y equals 2. It hits the y-axis at 2. And if you see the graph, again, it always gravitates toward those asymptotes. Okay, it goes toward this one, and it goes toward this one. This one heads toward this vertical asymptote, and it heads towards this vertical asymptote. And this side, it shoots up toward this vertical asymptote and kind of heads down towards this horizontal asymptote. So even though there's 3 separate parts, they all gravitate towards those asymptotes, which is really cool. And this one had zeros at -1 and +1. So there was a lot going on with this epic graph, but it was totally worth it. Because this graph is insanely awesome, right? Am I right? I know I'm right. So, just accept it. It's the coolest graph ever. Alright, now the final thing we're going to be talking about in this section is something called a hole. Which holes are these sneaky little ninjas in the graph that you cannot see, but are secretly there, and they're basically a little space in the graph. So what you're going to see, a hole, basically you're going along in the graph, you're going, and then all of a sudden there's nothing there. There's a little gap, and then the graph just keeps going. So there's kind of like a little hole in the graph, okay, like a normal hole. Okay, so if a rational function has a common factor in the numerator and denominator, so if you see the same exact factor in the numerator and denominator, and you can cancel it out, that is where a hole is. And whatever gets canceled out, you set that bad boy or that factor equal to 0. So like if you look at this one, do you see any common factors in the numerator and denominator? Holy hot dog, there's one right there, x minus 2. So it will cross out, which that is where the hole is. Whatever cancels out is the hole. Okay, so now there's a hole at whatever canceled out, which is at x equals -2, or x minus 2. Okay, and you set that thing equal to 0 and solve. Okay, so whatever factor cancels out, set that thing equal to 0, solve, and bam, there's a hole at that point. So if you see here, when we solve this, we get x equals 2. So if I go to where x equals 2 on the graph, if I go up here, there's a hole. So the graph's like going, and then you fall down the hole. Oh no. And be careful, you guys. Demon cats hide underneath holes. So you better be careful when you're on a graph with a hole. So you kind of need to skip over the hole and keep going if you want to save your life from the demon cat. Okay, so holes, again, are where things cross out. And then, after you cancel out the factor, whatever's left over, that's when you identify vertical asymptotes and zeros. Vertical asymptotes and zeros, although they do occur in the numerator and denominator, have nothing to do with the hole. So you ignore the hole, and anything left over, if it's in the numerator, you set that bad boy equal to 0 to find the 0. If it's in the denominator, you set that bad boy equal to 0 to get your vertical asymptote. So, in these last problems, final problems of the whole section, you guys. Holy hot dog, right? Okay, so in this one, we'll be combining everything we've talked about in our standard rational form. We'll be finding horizontal asymptotes using those 3 nifty properties. We will be looking out for holes by any factors that cancel out. And then whatever's left over afterwards, anything left in the numerator, we set those bad boys equal to 0 to find our zeros. Anything left in the denominator, we set those bad boys equal to 0 to find our vertical asymptotes. Are you ready for the most epic problems of the day? I'm totally ready. Go ahead and pause the video and watch example 14. So guys, I have to show you the graphs because I love these graphs. Okay, so this one, it isn't very exciting because a bunch of stuff crossed out and we weren't left with a whole lot. So there wasn't any horizontal asymptote based on our rule when the numerator is larger than the denominator. And if you see, your graph doesn't really gravitate toward anything horizontal. There was not any vertical asymptotes because nothing was left in the denominator after you crossed everything out. Our 0, we did have something left in the numerator, so our 0 is right here at x equals 2. And we had a sneaky little ninja. We had a little hole at x equals -2. So if I identify where x is -2 and then go down to my graph, there's a hole there. And that's where the graph is undefined. It doesn't work. Okay, because it doesn't equal the graph because it's an open bubble. So the graph's going, going, going. Make sure you hop over the hole or you'll fall to your death in the demon cat. Basically, it's where the demon cats live. So it's like the demon cat lair. So I would not fall in the hole, you guys. So hop over the hole and then keep going. Cool, right? All right. Example 15. If you think you understand it, go ahead and pause the video, try it on your own, and see if you get it right. Otherwise, follow along, and we're going to have a jolly old good time while we solve example 15. Oh man, you guys, example 15 had a lot of wonderful and magical things going on. Okay, in this one, we had everything. We had a horizontal asymptote at y equals 1, which if you see here, we have a horizontal line that hits the y-axis at 1. And the graph's going to head down toward that line on both sides. This one heads up toward it, and this one heads down toward it. We had a hole at x equals 2, so if I go over to where x equals 2 and go up to my graph, there's a hole there, which that's where the graph is undefined, so be careful. Okay, and then there's a vertical asymptote at x equals -1. So there's a vertical line that hits the x-axis at -1. And again, the graph gravitates toward it. So it heads up toward it there, and it heads down toward it there. And then we had a 0 at x equals -3. So right here, the graph hits the x-axis at -3. I'm sorry, guys, but that's the last graph I have to show you in the Prezi. And that's actually the end of the Prezi. I hope you guys enjoyed rational functions as much as I did. I think they're super cool, and I think they have a lot of really interesting and neat characteristics. So I hope you guys enjoyed it as much as I did. Thanks, you guys, for following along with me. I had so much fun.